Okay, so first of all, I would like to thank the organizers for giving this opportunity to present our work here. Some of you have already heard this talk at another place, so sorry if I bore you. So I will be talking about some patterns in scattering amplitudes. Okay, I'll be mostly talking about the color structure, color patterns. But before I do that, I want to first make a case that why QCD is important and why scattering amplitudes are important, QCD scattering amplitudes, and why infrared structure of QCD scattering amplitudes are important. So first few slides I would devote to that. So that's the first major scattering experiment by Rutherford. He was bombarding alpha particles on gold foil, and in fact, very recently I visited a experimental facility where they have, among many setups, one setup for Rutherford scattering. I wanted to show that picture, but the file became too big and I couldn't, so I had to remove. But that was quite impressive. Yeah, we have that in Hyderabad, not in IIT, but another institute. So we have been scattering particles, and after we have scattered them for long enough, we realize that the nature is governed, if you leave out gravity, by SU3 cross SU2 cross U1. Okay, that's the standard model of particle physics. And in this talk, I will only be talking about SU3. So that's the experimental slide for me. Now, QCD is actually extremely important, and this slide, this graph, um, establishes that very nicely. Imagine that this plot was not available. This was not done by these three groups, and we had discovered a peak in diphoton channel that we eventually did, and there is a signal standing there, and we have a leading order result with us, or even a next to leading order result. Okay. It would be very tempting to believe, and in fact, that would be the immediate conclusion, that what you see as a peak there corresponds to a new physics discovery. Okay, because you anyway did not know where you are going to see Higgs, right? You see a peak. Your cross section has no connection with the experimental, the measure, the calculated value. Suppose you had only leading order result or next to leading order result. So you see something very different from your prediction, and you immediately announce you have seen a new physics signal. So this slide tells you that it's not just about precision. Also, you may falsely believe something to be a new physics signal if your predictions from QCD are not precise enough, okay, because the couplings are larger. So that's why we have to uh, be as precise in our predictions as we can, uh, so that we can make proper understanding out of our experimental findings. So that sets the stage for me to look at scattering amplitudes in QCD. This slide is mainly for notation. A stands for amplitude, N for the number of external lines. Okay, so here it's N is 4. It could be any number of external lines, and I'm going to be talking about fixed number of lines. So all the corrections that you are going to have here are virtual. So no real emission lines coming out of those, okay, because that will change the number of lines. So I'm interested only in virtual corrections and actually in gluonic corrections. Okay, so I'm interested in QCD scattering amplitudes, but in infrared limit. So I have fixed number of lines, n number of them. And when I look at QCD corrections, they are all virtual particles running around in loops. Let's look at gluons for example. I have to do integral over loop momenta, and some of those configurations will correspond to soft gluons. Okay. Now, if you have soft gluons, propagators can go on shell. They may or they may not, depending on from which line they are being emitted. And if they do go on shell, then you have a divergence. Okay. So this object is divergent. It will have poles because you will calculate in dimensional regularization. So it will have poles in epsilon. Okay, but you might say, why should I care? Because after all, in any physical observable, these poles are going to be cancelled against real emission contribution. So why should I be so much bothered about it? It's just a technical detail. Okay. So here I list the reasons, and I will also show you one result to make the case that even though these poles are going to cancel, they leave behind very important, significant signatures at every order in perturbation theory. Okay. So they leave behind large contributions at every order in perturbation theory, even after the cancellation has happened, and you might be required to do resummation. Okay. If you do that, you recover predictive power. Otherwise, you have lost your predictive power. So here I'm showing how things will appear. So instead of looking at virtual gluonic emission, this K denotes a gluon here. I'm looking at a real emission. Just because the stories on both the sides are same, I'm just taking liberty to show it with a real emission diagram. So you see, if K, the momentum of this gluon, is soft, then this factor, which is called iconal current, diverges because it's 1 over K. Okay, so that is what leads to these poles when you calculate. Another important thing to note here is there is a factorization of this iconal current or the contribution coming from the soft gluon from what I call as hard part, this red block. Okay, so these two pieces sit factorized, and the same happens for collinear emissions also, or collinear addition when you're looking at virtual corrections. Okay, so I'll try to make a case using this plot. This is from my first paper on resummation from 2013 or 14. So the red curve here gives PT distribution for Higgs production. Okay, the details are not important. Which process, what, those are not important here. We are looking at PT Higgs produced in the final state and transverse momentum of it. Okay, suppose you do only a fixed order next to leading calculation. This is the blue curve that you get. Okay, so here let's say when you are at 250 GeV or 300 GeV, your result is somewhere around 10 to the minus 6. Okay, in whatever units it is, 10 to the minus 6. But as you go closer to 100 GeV or 50 GeV or so, it's 10 to the minus 2. Okay, so there's a 4 orders of magnitude difference. It's a huge difference. Now you would imagine that in experimental setup, the data is largely going to be around small values of PT because cross section is large. So you'll be producing a lot of Higgs with lower values of PT. This is what your blue curve is telling. But it is also telling you that you cannot trust perturbation theory precisely in that region. After all, it has taken jump of 4 orders of magnitude and it is going up, and actually it blows at PT equal to 0. So it goes to infinity if you do a fixed order calculation. Okay. So the place where your experimental data is going to be significant, you would like your theoretical prediction to match with those to make sense out of it. Precisely there, you cannot really trust your perturbation theory. Okay. And this has happened because of the contributions coming from soft and collinear emissions, which poles cancel, but the left imprint, and that imprint is showing up here. Okay, but that imprint is in a very specific pattern, and if you know that pattern, then you can look at the entire perturbation series, sum up all the terms, and get this red curve. Okay, that's a resummed curve, and you see here, now you are in good shape because you can use your experimental data and match with experiments and do whatever analysis you can. Okay, so resummation brings predictability back on the table, and for that we need to understand infrared structure of gauge theories in a proper way. Okay, so here is the plan of the talk. I'll be talking about scattering amplitudes in the infrared limit, and I will show you how webs enter into this discussion. Then I will tell you about a uniqueness theorem that we proved and a new formalism that we gave to look at the color structure of scattering amplitudes. And then I will summarize and the results I'm going to show you are based on this series of papers that we have uh, been working on since 2018. Actually, there are a few more now. Now, all that I told you in previous slides is possible. This resummation, etc., is possible because when you look at the amplitude in the infrared limit, A is going to factorize in that form in that limit. Okay, so it will have a piece which is called a soft function which carries all the poles in it. Okay, then a jet function which carries all the collinear information, and a hard function which is basically a matching function. So the important thing for me in this talk is the soft function. Okay, the matrix which contains all the soft divergences. I call it soft matrix or soft function, that you can write it down as a correlation of Wilson lines. So all these external lines which are hard particles undergoing scattering, you can replace them by Wilson lines to capture the soft divergences. And here is the most important slide of this talk. Okay, even if you were to forget everything what I say, this is the important one. You want to know the divergences. Okay, the soft function carries all the divergences which are living inside this. So this has poles in epsilon. You calculate it to some order in perturbation theory, you get those poles. Okay. On the right hand side, you have an exponential of something. That exponential of something has a gamma. Gamma is what is soft anomalous dimension or soft anomalous dimension matrix, the same we study when we do renormalization. Okay. That's a finite object, depends only on the directions of these external momenta. Okay, beta i's are giving 4 velocities. Okay, this is finite. The argument of alpha s, this depends on alpha, it's a series expansion in alpha s, has lambda square. Okay, this running coupling is integrated over. So you see there's an integration over lambda, which is the argument of alpha, which is going to generate the poles. So all the poles on the left get generated by this integral. Okay, but now it's an exponential here. You do a first order volume calculation of gamma, you get something at order alpha as one pole. You are exponentiating it, you get infinite set of poles at each order in perturbation theory. So what you are doing is, by one calculation at one order alpha as lowest order, you are able to, because of this formula, you are able to tell what is going to be the infrared structure at some level to all orders in perturbation theory. Okay, this is an example of resummation. Okay, so gamma is soft anomalous dimension or soft anomalous dimension matrix, and you would immediately agree that that's an extremely important object to calculate, because that gives you a control over poles to all orders in perturbation theory. Okay, so that's a center point of this talk. Here is what you get when you calculate gamma 1. Okay, there is a alpha s you have to supply, put it in the exponential, and you will be generating poles. Now, this S is the same soft function which has all the poles. This is sum of Feynman diagrams, and each Feynman diagram has its kinematic factor, corresponding kinematic factor, and a color factor. Okay, so at each vertex you have these generators of SU3, they are sitting there, so that contains the color factors. Now, this soft function can be written as an exponential of something, and that something turns out can be again written as sum over the same set of diagrams. Now, that's non-trivial. You can always write something as an exponential of log of itself. Okay, but it turns out that that log of S, again, it is a sum over the same set of Feynman diagrams with the same kinematic factors, but slightly different color factors. Okay, C tilde. And that's what is the important object for me. That's what we are going to calculate. And these are the papers in which these calculations were done before us, up to 3 loops, 2 and 3 loops. Okay, and we did also at 3 and 4. So this C tilde is important. People are interested in calculating this object, and the most difficult part here is K, the kinematic piece. Okay, so we are going to look at C tilde, and I'll tell you why C tilde is going to be useful. Okay, so the soft function is an exponential of something, and that something has a diagrammatic expansion, uh, uh, expansion, and that can be further organized into smaller sets of what we call webs. So here is a definition of a web. It's a set of diagrams closed under permutations of the gluon attachments on Wilson lines. So let's look at this one. If you permute these two attachments and these two attachments, in total you will generate 4 diagrams. If you take any of those and do that permutation again, you will be within that set. Okay, that's a web. That is what sits in here, and here I am just expanding over all the webs. So color factor of each diagram in the web times modified color which is C tilde, and C tilde is R times C. Okay, C is a column vector, R is a mixing matrix. Okay. So that's the mixing matrix that I am interested in calculating. How am I doing with time? 10 minutes. Okay, I think then let's go. These mixing matrices have important properties. One is that they are projectors. So R square is R. If you take a mixing matrix and sum all the elements of row, you get 0. So it's called row sum rule. And if you take mixing matrix column, any column, and each element you multiply with the corresponding S factor, then you get 0. Okay, and if you sum them up, you get 0. So here is how you find that S. So S is the number of ways in which you can shrink these gluons to the origin. So let's look at this diagram. If I try to first take this gluon to the origin, it encounters this gluon here, this attachment here and that attachment. So that's not allowed. When I push to origin, it should not encounter anything. So this one you can take first to the origin, then this one, and then the right one. Okay, or first take the bottom one here, then the top one, then the right one. So there are 2 ways, and that is what gives you S equal to 2. Okay, so that is what enters the column sum rule, and there is this theorem that you will get when you look at the eventually the color contribution coming out of it. It will correspond to a fully connected diagram. Okay, unlike here where these are all disconnected parts, this is fully connected. Now, one of the, apart from getting mixing matrices and knowing about the color structure, there's another reason why I believe this work which I'm telling you is useful. So kinematics is difficult. Okay, I'm telling about R that I'm going to calculate. C, you know. Okay, now this R I can diagonalize. So I introduce y inverse. I can diagonalize. Okay, because it's a projector, it will be, the eigenvalues will be only ones and zeros. Let's put that y here. Okay, and because some of these eigenvalues are 0, your I will run from this one to that one, and this is finally what you get. Okay, since I know R, I'm going to calculate explicitly. I know Y, the diagonalizing matrix. I know Y inverse, and since it is only this kinematic contribution which enters finally, probably a knowledge of Y or R can provide some simplifications on the kinematic sector. Okay, which has been which is turning out to be too difficult to manage. Okay, so that's also one hope that these studies will provide an indirect handle on kinematics. Okay, so I'm slightly going to change the diagram. So now the tail ends meet at origin. Okay, so instead of having this V kind of line diagram, you have this. So it's understood that the tails meet at the origin. Okay, it just makes easy drawing diagrams. That's why we have done that. So here is a result from our very first paper on this subject. I'm just quoting result for one of the webs. Okay, it has these gluons attached. You get this mixing matrix. Okay, you diagonalize it, and you find that the rank of this mixing matrix is 3, and that's the exponentiated color factor, which corresponds to fully connected diagram, as I was saying before. And then, of course, there are many more webs, and this was published in JHEP. And then after we had these 2 papers, we started noticing a pattern. I'm just showing few of them. So if you look at this R, okay, this block seems to be scattered around in many of the webs. Okay, if you calculate their web mixing matrices, you'll see the same pattern repeating over and over again. For example, this R also appears scattered here. Okay, so both of these, the top ones, they do not have any zero elements in them, and they appear to be scattered around in other webs that which we calculate. And these were done explicitly, these computations, using our in-house mathematical code, and that's the only code that is available which can do calculations to these orders. So we wanted to find out what if there is some pattern to be discovered, and in that quest we found we had an organizing principle in mind, using which we found that within a web there are webs. Okay, and also we proved a uniqueness theorem that you will soon see that is very powerful in telling the structure of these web mixing matrices. So we started by classifying diagrams. So we said if S is 0, meaning there is no way to shrink all the gluon correlators to origin without disturbing other ones, then it is 0. And if you can shrink in one or more ways, you call it a reducible diagram. Okay, and then we further classified them into partially entangled and completely entangled. And of course, there is nothing for here, and these are the corresponding diagrams. And then we defined something called normal ordering. So we order the diagrams in this fashion. First, I put completely entangled diagrams, followed by partially entangled, and the reducible diagrams. And immediately, I see that the R matrix takes this form. Okay, there are some places where null matrices are appearing, and then here an identity matrix appears. There is a D matrix, about which I will talk more, and then you have these two rectangular matrices appearing. Okay, so at least I know a reason why O's, zeros and ones are coming. Okay, I can tell you later if you are interested. And then we proved a uniqueness theorem, which simply says this: if you have a web for which S is not equal to 0, okay, and then you find out the S values for that web, and if you were to find another web, no matter at what order, okay, at higher orders also, with the same S values, then you don't have to calculate the mixing matrix. It will be the same mixing matrix as you have found at lower orders. Okay, so that's something we proved, and it is actually very useful. So as I said, even if the two webs are of completely different orders in alpha S, if the S values are same, the mixing matrices are same. Okay. Now we use the known properties of R and this form which we got after putting things in normal order, and then using that we could show that this D itself satisfies all the properties that a mixing matrix does. Okay, so you find a web inside a web. Okay, and then you see if that is a web, and typically it will it will correspond to S non-zero values. The diagrams will have S not zero. Then if you know from any lower order computation mixing matrix, okay, which has same S values, you can take that matrix, plug it in here, that part is done. Okay, so this way our D block is known. This identity matrix we know when it will appear. These are anyway null. These three pieces are still unknown. Okay, so that's what I said. So we introduced fused web formalism. Basically, this is a slide from some conference. That's why this wheel is there. So what we are doing is we are going to do some coarse graining. Okay, so here, for example, you have some diagrams from a web. These are entangled. That one is partially entangled. I just club them together to form this one. These two are entangled, connecting these three lines. So I just replace them by this correlator. This one, the top one, is not entangled with the lower part, so that remains there. This one is replaced by this. Okay, so that's what we did. That's what we did, and here is the outcome of that. Okay, so I'm showing you a sample here. So we took a web. You take a web which has 12 diagrams. Okay, run that fuse formalism, and then this mixing matrix using this fusing and using the previous ideas which I have shown earlier, you can show that all the diagonal blocks you are able to reproduce correctly without any explicit computation. Okay, so here you have a 2 cross 2 identity matrix. These are null. This is a 2 cross 2 matrix corresponding to S values both being 1, the same here, and this is a D matrix. Okay, so I know this completely, and here you get this result from a complete explicit computation. Okay, now we don't have control over all the elements, but just knowing the diagonal elements is enough to tell you about the rank of the mixing matrix. So I can now tell without any explicit computation the rank of the mixing matrix. Okay, which also means that I can tell you the number of exponentiated color factors that are going to sit in the exponent for the soft function. So soft function will be written as exponential of something, and that something will have objects which will have color structure of uh, an object which is fully connected, which doesn't fall apart if you remove the Wilson lines, and I can tell you the number of those that will appear. So here we are. We started with this, and we are here now. Okay, so that A block also, all the white pieces I know, okay, either from lower order computation or they are just identity NL blocks. These are the parts which I do not know, and I still do not know about them. Also, another thing that we could do was, because of this understanding, we could look at certain classes of diagrams to all orders in perturbation theory. So these dots mean any number of attachments, and we could just write down explicitly what their mixing matrices would be based on our ideas. So for this one, we have this mixing matrix completely known. Doesn't matter what order of alpha s we have. And similarly, for another class, we could completely write down the mixing matrices. So with our idea of fused wave formalism, which is a fancier fancier adjective for coarse graining, at 4 loops, we could predict 60% of the mixing matrices, the diagonal blocks for them, and 50% of all matrices, okay, just by doing that. Yeah, thank you. Okay. So here I summarize. Using our fused wave formalism, we can obtain diagonal blocks of R, and with that I can tell you the number of exponentiated color factors and the rank of the mixing matrix. Okay, diagonal blocks are either identity matrices themselves or something coming from lower orders. Okay, and we could also make predictions in some cases to all orders in perturbation theory, and then we later also applied to a case of massive Wilson lines, which I have not talked in here, and I think it will be nice to go back and okay, I should have stopped there itself. Yeah, here. Now you see, I have a very good control over R, the mixing matrix. Not full, but quite a lot. If I had full control over R, I knew everything about R, I would have known everything about Y, and then probably I can say a lot about K, okay, the kinematic piece, which is appearing to be very difficult to at present calculate. Okay, with that, I will thank you for your attention.
So questions, please.
Yeah.
Does this kind of structure that you have, the exponential part also having the same structure as the normal amplitude, does this depend on the choice of your propagator, what propagator you use? And
No, this doesn't depend on that. No.
so it can be also done in finite temperature field theory when
Oh,
one has a
I don't
little
think
bit
I-
different propagator.
I don't think I will be able to answer that. No, I don't know.
Because there the infrared divergences are also severe and one needs a resummation.
See, this is coming from factorization. Do you have factorization there also?
Yeah, in some cases, yes.
So it could could be something similar should happen, but I don't remember the details which I can check and say whether it will happen or not. But that's a nice question. Yes.
Well, thanks. So these webs, have I understood right? It's something that you've factored out as the color part of the diagram, is it? Is that, or have I got it completely wrong?
You have got slightly wrong. So let me go to web. Okay, before telling what a web is, let me just tell you why we are talking about it. This is the soft function that contains all the soft divergences in the infrared limit of your scattering amplitude. Okay, that soft function I can write as exponential of something. Now that something is actually a set of Feynman diagrams as I write here. It's still the same set of Feynman diagrams. Okay. Now, suppose you have a large number of Feynman diagrams that are going to sit in the exponent. Now, you take one diagram, one of them, and start permuting the gluon attachments. Okay, you generate, let's say, 7 or 8 of these, and so you identified which 8 are. And whenever you permute a gluon attachment in any of those diagrams, okay, you remain within that set of 8 diagrams. But there were many more. So your the entire set of diagrams has now broken into smaller sets of diagrams which are closed under these permutations.
Okay.
Each such set is a web,
Is a web. Now I understand.
and it has both the kinematic part and the color part, modified color.
It has both. Okay. My second question is, the when you say that the collinear and soft parts factorize, is there no term which has collinear divergence times soft divergence?
There
Is there, right?
There are. So here, that is why.
I mean, not at leading order, but at higher orders. It's obviously.
See, these are what gives you double poles, right?
Yeah, correct.
Even at one length.
Correct.
So here you see this jet function, for example.
Yeah.
That is capturing a collinear part. Okay, but soft is also here in Ji and also here.
Yeah.
So that's why you have divided the jet function by the iconal part to remove the double count.
Yeah. So that then my question is that even then this web thing works, is it?
You-
The web thing doesn't care about whether you have collinear or soft divergences, is it?
No, it is about soft.
It's about
See, this
okay.
this expression is for soft.
I see. I see.
So collinear will have its corresponding thing, but this is all about soft.
So okay. Thank you.
This exponent of the soft function, you have to include all the diagrams, right?
Fair.
When you have to write this S soft function as exponential of gamma matrix.
Yes.
So there you have to include all the diagrams.
Okay, go ahead.
So I want to ask, like you said, you have to take only gluons in the loops. You can take quark loops also, no?
Yes, there will be. I am looking only at gluonic contributions.
But that means you are not looking at full S, you are looking at sub part of that S.
Yes. So I'm not looking at soft quarks. Okay. Soft gluons are going to give you the leading contributions. Soft quarks give you
But it can,
subdominant contributions. Okay. So I'm looking at the
because there in the propagator there is P upon P square. That's why.
So you can take, for example, any diagram which has a quark line coming out, okay, and you will see that when you do the calculation, that the fact that you have a U or a U bar sitting there provides an additional factor of additional numerator. So your naive power counting of having a K below is disturbed because of the U's, which is not case for gluons.